130 people descend beneath the ocean, sealed inside a pressure hull of steel. Once the hatch closes, they'll spend the next 3 months underwater with no fresh air and no escape to the surface. Every breath must be created, cleaned, and reused. But here's what most people don't realize. The biggest threat to a submarine crew isn't enemy torpedoes or crush depth. It's the air they breathe. When ventilation systems fail, submariners have minutes to live. And in 1963, that's exactly what happened to 129 American sailors. On April 10, 1963, the U.S. Navy nuclear submarine USS Thresher disappeared beneath the North Atlantic during deep diving trials. 129 sailors and civilian technicians went down with her, the deadliest submarine disaster in U.S. history. All 129 crew members and civilian technicians aboard were lost when the vessel sank to crushing depth. This was a tragedy that was not caused by combat, but a cascade of mechanical failures, including a critical life support and ventilation-related problem. But this wasn't enemy action. This was a cascade of mechanical failures that started with a single pipe joint rupturing in the engine room. High-pressure seawater sprayed onto electrical systems, causing shorts that triggered an automatic reactor shutdown. Instantly, the submarine lost all propulsion and power. Without thrust to drive upward, the crew tried to perform an emergency ballast blow. This was a procedure that forces high-pressure air into the ballast tanks to expel water and make the submarine buoyant. But the worst part of this accident was the high-pressure air system, which served atmospheric and mechanical roles. Ventilation was the main cause of the USS Thresher disaster, as moisture and ice got into the air pipes and blocked airflow, preventing the crew from blowing the ballast tanks and surfacing after an initial engine room flooding. Then, the leak in the engine flooded the space, causing the reactor to shut down. The compressed air system failed because of ice, causing the submarine to fatally descend and then implode at extreme depth, killing everyone aboard. In the wake of this disaster, the Navy determined that the piping failure that started the domino of events that caused the submarine to implode. Because of this, the U.S. Navy had to create the SubSafe program, which focused on protecting the integrity of ventilation and life support systems. But how do submarines ventilate 130 people trapped underwater for 3 months? Well, that's with a method called closed-loop air life support systems. Before we go any further, if you're finding this deep dive into submarine disasters and life support systems fascinating, take a moment to like the video and subscribe to the channel. We break down real military incidents, hidden engineering systems, and the technology that keeps crews alive in the most extreme environments on Earth. And coming up next, we're going to reveal how submarines actually create breathable air from nothing for months at a time. Closed-loop air life support systems. A modern nuclear submarine is its own sealed ecosystem, capable of supporting a crew for months by recycling and regenerating the air inside its hull without even breathing the outside ocean. Unlike a surface ship that depends on open air, these vessels create and purify their own atmosphere. This allows them to remain submerged for 3 months without surfacing. At the heart of this closed-loop life support system is oxygen generation. Nuclear submarines use electrolysis, splitting purified water into oxygen and hydrogen using electrical current from the reactor. The oxygen gets pumped into living spaces, replacing what the crew breathes out. The hydrogen? That's either vented overboard or, on some boats, recombined with CO2 to make water again. The oxygen produced is introduced into the submarine's living spaces to replace the oxygen consumed by the crew's respiration, while the hydrogen byproduct is safely vented on board. Some submarines also carry chemical oxygen generators, oxygen candles. These solid chemical blocks release oxygen through controlled combustion. If the main electrolysis system fails, these candles can keep the crew breathing while repairs are made. But generating oxygen is only half the challenge. As the crew breathes, carbon dioxide accumulates. If this becomes elevated, the air in the submarine can become toxic. To handle this, submarines employ CO2 scrubbers, which are machines that chemically absorb carbon dioxide from the circulated air. Many systems use solutions of monoethanolamine, which binds CO2 and later releases it when heated, so the gas can be compressed and discharged overboard, allowing the absorbent to be reused. In emergency or backup situations, submarines might also use consumable absorbents like lithium hydroxide to chemically trap carbon dioxide from the atmosphere. Maintaining breathable air also requires continuous purification and circulation. Ventilation systems push air through filters and treatment units that remove moisture, CO2, and other contaminants, such as carbon monoxide, hydrogen, and particulates. Depending on the submarine, some systems can oxidize harmful gases into less dangerous compounds before they are removed. And advanced atmosphere monitoring equipment keeps track of gas concentration throughout the vessels in real time. All these components work together to offer life and comfort in a place where fresh air doesn't exist. But it doesn't always go well, like the shocking USS Thresher disaster. It's not always as devastating, as in 2011, another U.S. submarine faced issues with its ventilation and eventually had to surface. If you find this pretty interesting, give us a like and subscribe before we go into the shocking cases of ventilation accidents in U.S. Navy submarines. But if submarines can manufacture oxygen, scrub carbon dioxide, and recycle air for months without ever surfacing, what happens when even one part of that closed-loop system breaks down in the worst possible environment on Earth? What do you do when you're trapped beneath solid Arctic ice, with no access to the surface, and your source of breathable air suddenly fails? And more importantly, how close did one U.S. submarine come to disaster before the world ever heard about it? In March 2011, the USS New Hampshire, a Virginia-class fast attack submarine, was operating beneath the Arctic ice cap during Ice Exercise 2011. The crew is running drills in one of the most remote and unforgiving environments on Earth when the oxygen generation system fails. At the time, the submarine was operating with its crew in one of the most remote and demanding environments a naval vessel could ever face. Early in the week of March 13th, the boat's onboard oxygen generation system failed, leaving the crew without its primary means of producing breathable oxygen deep under the ice. The malfunction in the oxygen generator forced New Hampshire to surface through the Arctic ice as the safest course of action. This is a complex and delicate maneuver in its own right, especially with the thick pack ice overhead. Until the submarine could break through and reach open air, the crew relied on backup oxygen candles. These are chemical devices stored aboard that produce oxygen when burned. This was how they sustained breathable air inside the vessel. This measure ensured the safety of the more than 130 sailors and officers on board, while they managed the emergency and waited for repairs. But they couldn't depend on backup oxygen candles forever. The submarine's parent company had to dispatch replacement parts and technicians to the temporary ice camp created for the exercise, so that the system could be restored and the submarine could safely resume operations. This revealed just how hard it is for submarines to operate in extreme environments, especially with their ventilation, oxygen management, and life support systems. Ever since that happened, modern submarines are designed with multiple layers of backup to address these failures, and have a lot of oxygen candles so that they can be protected when the main systems are compromised. Fortunately, no one got injured or lost their lives after this event. But when ventilating 130 people underwater for 3 months, the submariners can't stop paying attention. They constantly monitor all the levels of oxygen, carbon dioxide, and gases to protect themselves and keep breathing recycled air for months. Stories like this show just how thin the margin for error really is beneath the ice. If you appreciate detailed, real-world breakdowns of military engineering and the systems that quietly save lives, make sure you're subscribed. This channel dives into the technology most people never see, from submarine life support to classified era design choices. And next, we're going inside the monitoring systems that make sure those 130 sailors know exactly what's in every breath they take. Modern submarines rely on continuous atmospheric monitoring and control systems, which make sure that oxygen levels remain safe and that dangerous gases never accumulate to life-threatening concentrations, even during months underwater. The basis of this is sophisticated gas analyzers and monitoring networks, which sample air throughout a vessel's compartments. These systems constantly track important components like oxygen and carbon dioxide levels, as well as potential hazards that can harm the crew members, such as carbon monoxide and hydrogen. Specialized analyzers, including multi-gas detectors and spectrometers, draw air samples from different locations and then deliver real-time readings to central consoles, so the crew members can respond to any abnormalities in the recycled air. One of the pieces of technology in submarines is the atmosphere analyzer. This measures dozens of different gases and provides regular data logs to support long deployments. Ships combine a redundant network of sensors to protect against single-point failures, and alarms are triggered if the levels drift outside of strict safety parameters. Rather than checking for oxygen depletion alone, they also check for trace contaminants and toxic substances, like refrigerants and combustion byproducts. The result is a dynamic, fully controlled environment. The U.S. Navy continues to improve its monitoring methods and protocols to ventilate all the crew members. In fact, when the U.S. Navy saw how the navies of other countries ended up with ventilation accidents, they decided to improve their response and protect submariners from shocking accidents. But even with constant monitoring, redundant sensors, and real-time alarms, history shows that air systems don't always fail quietly. Sometimes, the danger doesn't come from suffocation at all, but from the very equipment designed to keep crews alive. But how did one under-ice incident force the U.S. Navy to re-examine how they handled breathable air at sea? In the aftermath of the 2007 explosion aboard the Royal Navy submarine HMS Tireless, a detonation of an emergency oxygen-producing candle that killed 2 sailors during under-ice exercises, the U.S. Navy closely examined its own oxygen candle safety and response protocols to ensure that its fleets didn't face a similar tragedy. The tireless incident happened when a self-contained oxygen generator, which was part of the submarine's backup atmosphere system, exploded in the forward escape compartment while the boat was operating with U.S. forces in the Arctic. It was forced to float to the surface for repairs. When the U.S. Navy faced this incident, they reviewed the design and safety of its oxygen candle furnaces and emergency atmospheric systems to confirm that American equipment did not suffer the same risks identified in the Tireless case. The Navy's evaluation concluded that the U.S. oxygen candle furnace design was fundamentally sound, and so if there was significant contamination with organic materials, it won't cause an explosion or the release of burning material from the furnace's current design. Unlike Britain's Tireless unit, which became contaminated with oil or another hydrocarbon, behaved erratically, U.S. systems had been engineered with safeguards against these hazards. The U.S. Navy is constantly improving its storage, handling, and inspection protocols for ventilation systems and oxygen generation. Their submarines also have more advanced emergency measures in case there's any unexpected situation. Submariners prepare for long missions and also worst-case emergencies, including situations where the vessel's normal air regeneration systems fail or internal conditions become hazardous. To meet this threat, modern submarines are equipped with a dedicated emergency breathing apparatus that allows crew members to survive in oxygen-deficient, smoke-filled, or otherwise compromised atmospheres. One of the key devices used by the U.S. Navy is the Emergency Air Breather System, which is a mask and hose assembly that connects to a network of air manifolds located throughout the submarine. When the internal atmosphere becomes unsafe, submariners wear their EAB masks and plug into the nearest manifold, drawing breathable air directly from the submarine's compressed air system, so they can continue normal operations regardless of the crisis. The emergency breathing systems are part of a broader suite of ventilation and life support tools, and submarine personnel train regularly to use them in low visibility or no light conditions. Sailors have to go through exercises like blindfolded EAB races so that they can locate manifolds and put on their gear quickly regardless of what happens. Submarines also carry other specialized respiratory protection for firefighting and contamination. It's these kinds of emergency equipment that are meant to prevent issues and accidents. And this is one of the reasons why the U.S. Navy submarines hardly ever have fatal ventilation events. But here's the twist. All of this emergency equipment and training only works if there's air left to use. That's why survival at sea isn't decided at the moment of failure, but it's decided months earlier in design reviews, material inspections, training drills, and maintenance logs. But the question is, why do U.S. submarines almost never have fatal ventilation events? Since the early days of submarine development, the U.S. Navy has built an exceptionally strong safety culture around life support and atmospheric systems. This is a major reason why ventilation or air quality failures have hardly ever resulted in fatalities on American submarines. Modern U.S. submarines have been designed with redundant, rigorously engineered systems that continuously monitor and control the internal atmosphere, keeping oxygen, carbon dioxide, and other gases within safe limits, even during extended submerged operations. Advanced atmospheric analyzers track major and trace gases throughout the vessel, enabling crews to detect and correct issues before they become dangerous. Another key factor is the SubSafe program, which came up after the loss of USS Thresher in 1963. SubSafe uses meticulous standards that aren't just for hull integrity, but also for any system important to survival underwater, like the life support and ventilation hardware. Every component must be traceable, tested, and verified before installation, reducing the risk of unexpected failures during patrols. In addition to technical safeguards, submarine crews undergo rigorous training in atmospheric monitoring and emergency response, equipping them to interpret sensor data and react swiftly if conditions deviate from norms. Sophisticated CO2 scrubbers, oxygen generators, ventilation blowers, and alarm networks operate in concert to maintain a stable environment, supported by built-in backups and manual procedures. Submarines are built to ventilate 130 crew members that are trapped underwater, even for as long as 3 months. Regardless of how long the submariners are underwater, the vessel continues to recycle oxygen and carbon dioxide, allowing the crew to complete their mission safely. What shocked you the most about the ventilation process of submarines? Let's know your thoughts in the comments. For more inside looks at life in the US Navy, hit like, subscribe, and tap the bell. See you in the next one.